Well, hello everyone. It's really great to welcome you all back to the physics department for the winter series of the University of Michigan Saturday morning physics program. I hope you all enjoyed the donuts this morning too. Yeah. I'm Roy Clark, faculty co-host of this event, along with my colleague, Professor Tim Chupp, who got the series off, the winter series off to a fabulous start last month with an amazing live link to the NASA International Space Station with astronaut and physicist John Cassada. And those of you who are part of the 650 plus live audience, or among the 1,800 or more online participants on January 14, will remember vividly Josh's inspiring message of hope for our beautiful yet fragile planet. I think you will find today's presentation very much along that theme. And the presentation is given by Adam Simon, Arthur F. Turnau, Professor of Earth and Environmental Science at the University of Michigan. And I think you'll find it equally global in its perspective and far-reaching in its environmental implications especially. Adam asked me to keep the introduction a little short, so I will do that. But I did want to mention that he is a distinguished luminary in critical material resources for energy critical materials that are needed for technology, especially energy technologies. And he has researched and lectured on all 7 continents of the planet, earning numerous awards, including the U of M's Provost Teaching Innovation Prize, and he has earned advanced degrees in geology and geochemistry. Following the presentation, we will have a live Q&A session, so I would ask you, as traditional, to email your questions to physics@umich.edu, and we will also have microphones for the audience, for the live audience, following the lecture. Now we're going to dim the lights so that our speaker can make his entrance around the back of the auditorium. And please give a really warm welcome to Adam Simon.
Whoa. It's actually darker than I thought it was going to be, but I'll make it. All right, so here's what I want everybody in the room to do. All right, I want you to think about waking up in the year 1800. All right, what would life have been like if you woke up in the year 1800? Right, what would the first thing in the morning you have done? How would you have put food on the table? What would you have needed to put that food on the table? How would you have provided energy to cook the food that you put on the table? Right, life today, in almost every place on the world, and there are certainly challenges, life today is different than it ever was. All right? So if you woke up in 1800, one of the ways that you would have provided energy for both light and also for heat would have been to use a fossil fuel. And your fossil fuels of choice would have been wood that you would have felled and chopped up and had in your house ready to burn, Or you would have had a candle like the one that here I have at the front of the room. And this is a tallow candle. You can buy them today on Etsy and other bougie websites. And tallow is animal fat. So to provide meat, you most likely would have had animals, or you would have known somebody who had animals. And periodically, you would butcher those animals, and you would consume the meat, and you would use some of the fat to fry the meat and add flavor. And then you would render the fat a liquid and then cool it to a solid, and you would put a wick in it, and you'd use a tallow candle to provide light. And that was it. That was it. Right? Those were your fossil fuels. If we think of animals, cows and sheep, when they're dead, they're fossils. And if we look at the data here, right, from left to right, you're looking at years, so 1700 through today. And what I want to highlight is that, again, if we go back a couple hundred years to pre-industrial Earth, you would have used candles made from animal fat. We then learned how to use coal to produce what we called town gas. We then decided that killing whales all over the planet and rendering the fat from whales to use as candles was a good idea. Then we figured out in the 1850s how we could use crude oil and extract from crude oil one of its components, which is kerosene. And kerosene lights became extremely popular because they were on demand, and they produced a lot of energy. And then we had a game changer in green. The game changer was electricity. And this is when the game changed for humanity. We used to have World's Fairs where scientists and others would display their new inventions. Right? We had World's Fairs where the hot dog was displayed, ice cream was displayed, popcorn was displayed, things that today we simply take for granted. And at the World's Fair in Chicago in 1893 was the first time on planet Earth that humans saw how electricity could be used to create artificial light so that at night we essentially could live as we did during the day. And if you've read the text by now, this monumental moment in human history, we had President Grover Cleveland, who attended the World's Fair, and after all the lights went out, he flipped a switch. And when he flipped the switch, current or charge flowed along copper wires and illuminated 100,000 light bulbs. And this is one of the original black and white images. We had not yet invented color photography. But that was a game changer. And trust me when I say every person who had access to a newspaper at the time and saw this image, every person said, "I want that." Every person. Only a few years later, there was another game changer. So if you go back to 1900, in the countries that we call the European Union today, the United States, Canada, there were more than 100,000 humans who woke up at that time 6 days a week and worked 12-hour shifts and only took off on Sunday. And every day, more than 100,000 people, went one too fast, woke up and made carriages for horses every single day. And the image on the left is New York City's Fifth Avenue in 1900. And here's how fast this game changer happened. The red circle is the only vehicle that's a combustion engine. Everybody else is riding a horse. 1913, no horses. Now, at the time, this was viewed as incredibly good for public health because horses defecate when they want to defecate. Right? They're not like dogs. They don't go to the door and go, and then you let them out. So one of the big public health crises in major cities around the world at the time, in more developed countries, was literally all of the horse that would leach into the subsurface when it would rain, because rainwater has a slightly negative pH, it's a little acidic, and all of the E. coli and other bacteria got into water supplies. So this was viewed as a major advance in public health. It was also important because it forever changed agriculture. So this is a black and white photograph of the way that we farmed in the 1800s. In the late 1800s, 75% of all US citizens were farmers. 75%, right? Today it's less than 1%. And why is that? Because from then to now, what used to take an entire day, 25 men, we do in 6 minutes. 6 minutes. So we went from producing agriculture at that time faster than we had ever done, and now we do the same thing every single 6 minutes. It's phenomenal. And that has allowed our global population to increase from roughly 1 billion people pre-industrial time to now we're 8 billion people and counting. And without a doubt, when we look at population increase and we look at lifespans, the average lifespan in the United States in the last 100 years has doubled. Doubled. That's phenomenal. Now that takes into account maternal fatalities, infant mortalities, childhood mortalities. We had no vaccines for anything 100 years ago. We couldn't cure cancer 100 years ago. There was no chemotherapy, no modern medicine. So without a doubt, these can be thought of as cause and effect. Our ability to grow food on a really large scale very quickly allowed us to provide food for the masses. And again, I recognize that there are still challenges. But by and large, when we look at our modern medical infrastructure, there are problems, but the technologies that we have available to us today allow for our lives to be better than at any point in human history. And we did that by transitioning from wood and tallow candles and whale oil to these 3 fossil fuels: coal, oil, and natural gas. And you can clearly see an almost one-to-one correlation that as human population increased, our consumption of fossil fuels increased in lockstep. And I'm going to play an animation now because I want everybody to have a sense of how much of these fossil fuels we consume. Right? Individually, we have some sense, if we still drive a combustion engine vehicle and we go and we put petrol in our car, how much fossil fuel we're consuming. But let's look at it globally here. Hopefully. I got to get rid of my laser pointer. Okay. So we're going to start in 1830, and you can clearly see up here on the top, in 1830, primarily we used wood. That was it. And a little bit of coal. And watch what happens. What you see is the displacement of wood, the displacement of tallow, the displacement of whale oil, and you see the incredible growth in consumption of oil, coal, and gas, which is natural gas, methane. And wood would be down here on the lower left. Now, when we talk about energy, it's important to distinguish between primary energy and secondary energy. Secondary energy is electricity. And politicians in the news media always get this wrong. Right? Electricity is a drop in the bucket of our total global energy consumption. And electricity is secondary because we use a primary fuel and then we produce electricity. So when we look at global primary energy consumption, all I want you to see here is that coal, oil, and natural gas, they dominate primary energy. They're 85% of global energy consumption, 85%. And the other 15% includes everything else. Everything else. To put that in local perspective, if you're a fan of football and concussions and other things, you all recognize that the Big House at capacity seats 115,000 people. Now, it's 10:46. If you came into this room at 10:06, globally, we have consumed oil equal to filling the entire Big House up to the top of the press boxes, and we have drained it, and we're restarting at 10:47. And in the next 40 minutes, we'll fill it and drain it again. So when you think about energy consumption, and oil is the #1 traded commodity on the planet, this is what we're talking about when we think of oil, right? The media likes to talk about we produce and consume 32 billion barrels of oil a year. But think about it in terms of the Big House, which we're all familiar with. Now, I said that global population has increased, and our consumption of fossil fuels have increased in lockstep. And most people would agree that life today is pretty good to what it would have been in 1800, 1700, 1600. Okay, there's a reason the show is called Naked and Afraid. I rarely meet people that want the naked part without being afraid. Okay? So, what are the downsides? Well, now you're going to look at an animation, and I want to highlight where your eyes should start, which is England up here. England is where the Industrial Revolution began, for a variety of reasons. England was the first country on the planet that allowed individuals to patent intellectual property. And if you have the ability to patent intellectual property, that means you own the property and you can charge a royalty when people use your ideas. So Thomas Newcomen, who invented the steam engine in 1712, patented the steam engine, and James Watt had to pay him to make improvements. England also had major seafaring ports, and it also had a lot of coal at the surface of the earth. It also heavily depended on slave labor in the United States, where Africans were brought to the U.S. and forced into slavery to grow cotton, essentially with no remuneration whatsoever. And that cotton went to England, and it's the direct result of slave labor and cotton production in the United States that allowed England's economy to grow. That's a cause and effect. Here you're looking at carbon dioxide emissions that we know the cause. So let me play this, and we start in 1751. England is the first country where we have evidence the Industrial Revolution happened. It made its way to the United States in the early 1800s, and you start to see the U.S. pop up in color. You see the diffusion of industry from England across the English Channel to continental Europe. So what you're looking at here are, in each place, game changers that forever modified how humans live. And I'm not assigning good and bad to that, but every time we see a particular place light up, we're looking at combustion of fossil fuels that are either directly being used to provide energy in that local area, or combustion of fossil fuels embedded in the products that we use. Now, how can that be bad? Well, here is global temperature from 1850. Red is hot, blue is cold. And what you see year over year is that global temperatures have systematically increased. Now, there's no expectation that they should have increased first in England, because when CO2 is emitted during combustion of fossil fuels, our atmosphere globally circulates, and that CO2 diffuses throughout the entire atmosphere. But these temperatures are real data. So when we're looking at these temperatures, and we just looked at CO2 emissions, right? If you're interested in exploring or testing the hypothesis that the emissions could be a cause for these increased temperatures, what would you do? But how would you test that? And they continue to get hotter. As anybody who followed the news last summer, first summer in recorded history where continental England exceeded 40.0 degrees Celsius, ever since we invented thermometers. Now, in 1982, a group of scientists working for Exxon, that's 10 years before Exxon acquired Mobil to become ExxonMobil, but a group of scientists at Exxon, like many groups of scientists around the world, they made the same observations. Globally, the concentration of CO2 in the atmosphere is increasing. Globally, the temperature of the atmosphere is increasing. And let's test the hypothesis that adding more CO2 to the atmosphere is the cause of increasing temperature. So they and many other groups did what we think of now as simple experiments. We are in a physics department, so this is a simple experiment. And what you're looking at here are two beakers. The one on your left is filled with CO2, and the one on your right is our normal air. And there are thermocouples in both beakers. The thermocouple that is colored red is on top, currently reading 24.0 degrees. And the thermocouple in blue, the bottom left, is air. So in 1982, scientists at Exxon did similar experiments, and what they were able to demonstrate unequivocally is that in any volume of air, as the concentration of CO2 increases, the temperature increases. There's no doubt. We have done this type of experiment now probably hundreds of thousands of times. So it's irrefutable. So in 1982, if I can go back to my slides, Monica, what the ExxonMobil scientists did is they said, okay, let's look at historic data. They looked back at 1959, lower left, and they knew the reported atmospheric concentration of CO2 was 316 parts per million. They knew in 1980 the concentration was 338 parts per million. So what the Exxon scientists did is they looked at that time, how much coal humans were combusting, how much oil humans were combusting, and how much natural gas humans were combusting. Because combustion of those three fossil fuels requires that you add oxygen, and that produces heat, energy, and carbon dioxide. Okay, it's an irreversible chemical reaction. So they then forecasted future consumption of coal and oil and natural gas and calculated what the concentration of CO2 would be in the year 2020. And they predicted it would be 415 ppm, and they were exactly correct. The scientists at Exxon were really, really smart people. So they tested cause and effect. They proved that. They then forecasted future CO2, and their forecast, their prediction became correct. And we understand well the concept of greenhouse gases absorbing energy. So what Exxon did, and the figure on the right is directly from Exxon, so it's their study. What they did is, on the x-axis is year, the left y-axis is the atmospheric carbon dioxide concentration, and the right axis is what should the temperature be at a particular concentration of CO2 in the atmosphere. These are their data, and what they calculated here is that as a function of time, left to right, and increasing CO2 concentrations in the atmosphere, temperatures should increase. And the two lines here represent the uncertainty on their prediction. Exactly as the Exxon scientists predicted, global atmospheric temperature in 2020 was 1.2 degrees warmer than it was in 1960. Exactly. Irrefutable. Now, that leads us to be able to predict if we do the same calculation that Exxon did in 1982, what's going to happen? So we can look at time on the x-axis in years from 1990 out to 2100 and total CO2 on the y-axis. And if I play this through, we're looking at what we can consider business as usual. If we as a global society continue to consume energy produced by combustion of coal, oil, and natural gas, then global atmospheric temperatures will rise somewhere between 3.2 and 3.8 degrees Celsius relative to pre-industrial temperatures. Right? The second option is that if we immediately stop combusting coal, oil, and natural gas, then global atmospheric temperatures will not rise by more than 2 degrees C relative to pre-industrial temperatures. Now, a lot of people look at these data and say, but Adam, it's so nice now that Michigan winters are warmer. I don't have to shovel as much snow. All right? So what could the impacts be for a couple of degrees C? So now what I'm going to show you are two images. Oh, we'll let it catch up to itself. Where the lower left is the current and predicted or forecasted production of corn, maize, and the upper right is the current and forecasted out to the year 2099 wheat yield productions. Red is bad. Sorry. I've got a Mac, so we know it's not my computer. I can tell there are a lot of PC people in the room on that one. Where are we? Okay, let's hope this plays. So red is bad. Yellow's bad. What do you see? What we see right now in real time are latitudinal migrations of crops. If we look at maize only here, look at the United States. By 2099, the United States, we won't grow corn. And that's because when we think of these crops that for us are simply ubiquitous, summer corn, they require relatively narrow temperature windows. Right? They need winter temperatures to be about the right temperature, and summer temperatures can't be too hot. The same thing for fruit. If you go to the state of Georgia, right, the state of Georgia is the peach state. 20, 30 years from now, Georgia won't be able to grow peaches because the winter temperatures will be just warm enough that it will eliminate the ability for peach trees to grow. So when we hear people dismiss, oh, it's only 1 or 2 or 3 degrees, it has global consequences. Because when we look at what we now call America's breadbasket, we won't grow wheat, we won't grow corn, we won't produce bread. So what do? Right? We've got choices. We can business as usual, we continue what we're doing, or we can think about alternatives. And one of the alternatives is to eliminate the combustion of fossil fuels that right now account for about 75% of global CO2 emissions. So that's one of the choices we can make, and it requires a number of things. It requires that we electrify everything. Now again, remember, electricity is a secondary form of energy, and we simply use coal and natural gas to produce that energy. The majority of the oil that we consume is for transportation, going from A to B and back to A. So if we electrify everything, that means we need other sources of energy to produce that electricity. And in order to reduce the potential for global atmospheric temperatures to rise by more than 2 degrees Celsius by 2050, we have to provide 90% of our global primary energy from renewable energy resources. 90%. So wind turbines and solar panels you can think of as primary sources of energy that will then generate the electricity that we consume. And we need battery storage at a local and a large scale, what is often referred to as a grid scale. So these are data for the United States, and I don't want you to squint. What I want you to see is right now, anything on here that's not a name in black or a black dot are where we currently have wind and solar sited. Not individual homes, but large-scale utility wind and solar. This is 90%. This is what we need. Now, when you look at that, you probably had a, whoa, that's a big change from where we are now to where we need to be. But remember, in 1900, everybody rode around on horses in New York City. By 1913, not everybody, but the middle class who had previously afforded horses and carriages didn't drive them anymore. They drove cars. So we have made this type of change on a shorter time scale. Now, the magnitude of the change is greater today, but humans have done this. So how do we do it? Well, as a geologist, when I look at wind, this is what most people see. This is what I see. I see all the metals that are required to build wind turbines. So when you drive anywhere and you see a wind turbine and you see the blades are spinning, yeah, sure. Why are they spinning? Those blades are spinning because natural gradients in heat in the troposphere create convection, and that is what we call wind. And as those blades are spinning, what do we get? We get electricity. And that's what we want. There's no combustion, there's no coal, there's no oil, there's no natural gas. But we're getting the electricity, which is what we want. Because ultimately, for all of us who have access to electricity at home and work, what's the number one thing that we want to do in the morning? We want to grab this and take it to the bathroom and make sure it's fully charged. Right? So that wind, those blades spinning, charges our phones and everything else that we use. But we need all of these metals. When you look at a solar panel, right, almost intuitively now we have a sense of, okay, solar panels allow us to charge things and to power things from the solar panels. So we've got up here 2 solar panels, and I'm going to highlight that one of them is really large and one of them is much smaller. And this is what solar panels do. In real time, when the sun is shining and incoming solar radiation is received by the solar panels, that creates a circuit, and we have a charge that flows, in this case, to the wind turbine to make it spin. And equally so, that could be a hot water heater. That could be anything else that we want the solar panel to charge. So when I look at solar panels, this is what I see. All of the metals that are required to manufacture solar panels. When I look at a battery electric vehicle, what do you see? In the news all the time, we're told that electric vehicles have lithium-ion batteries. That's the current choice for electric vehicles. And what I see is that every single battery electric vehicle needs 25 pounds of lithium. So think about the last time you bought sugar in a 5-pound bag. 5 of those lithium are in a battery electric vehicle. Every single battery electric vehicle. But battery electric vehicles also have 200 pounds of copper, 60 pounds of nickel, 44 pounds of manganese, 31 pounds of cobalt, and 5 to 11 pounds of rare earth elements in every single battery electric vehicle. In the United States, we currently have a goal that 50% of all vehicles sold in 2030 will be battery electric. In the United States, we produce and sell about 16 million cars every single year. So this is 8 million battery electric vehicles by 2030. And our former governor, Secretary Granholm in the DOE, almost by the hour, if you follow her on Twitter, there's something coming out of either Granholm's office or Jigar Shah's office about battery manufacturing facilities. And again, I hear that and I think that's great. We have all these battery manufacturing facilities. Jigar Shah has something like hundreds of billions of dollars at his disposal. And we then look at other places. The European Union wants 100% battery electrics by 2030, 100%. So if we think about that through my lens and the metals that we need for 8 million vehicles, it's 200 million pounds of lithium, 1.6 billion pounds of copper, 480 million pounds of nickel, 352 million pounds of manganese, 248 million pounds of cobalt, and 40 to 80 million pounds of rare earths. Now, whatever quantity you choose to use, that's a lot, because this is all new metal that we currently don't have access to. And on the right, just for scale, I include the current US production from mines. Notice that manganese, we produce 0. All of the rare earth elements that we do mine, and they're only a small amount, from one mine in California, we ship them to China. And China does 100% of the processing. We do a good job on copper, but all of this copper is spoken for. So it's not available for the 1.6 billion we need for battery electric vehicles. So I'm going to focus for the next few minutes only on copper. Right? We need 1.6 billion pounds of copper, and that's for only 50%. In order to have 100% of our vehicles, it's 3.2 billion pounds of copper, and all of these other numbers double as well. And then we have the European Union, and China, and Japan, and Australia, and India, et cetera, et cetera, et cetera. So you're going to see here data plotted as a function of, on the y-axis, is millions of tons of copper. So just think bottom left is 0 copper, and increasing on the left y-axis is copper. And on the x-axis is time. And what we're looking at are real data for 2017 through 2022, and then forecasted data to 2035 based on the stated policy goals of the United Nations, their Sustainable Development Goals, the Biden Build Back Better administration, and the European Union. So we're using all of the goals that the UN, the US, and the EU say they want to achieve. Here's the global copper demand over the next 15 years. And here is the amount of copper that currently operating mines around the world, the whole world, will produce over the next 15 years. Do you see a problem? Now, there are some proposed new mines, and if they are permitted, and if they start to produce copper, they can help make up a little bit of this. But here's the problem. We have a huge supply gap, deficit. It doesn't matter how many battery electric facilities Jigger and Jennifer build. Doesn't matter. Those battery electric facilities will literally be idle without copper and all the other metals. Can't make a battery if you don't have the ingredients. It's literally not possible. So we have a problem. And it's not just for copper. If you look at this schematic of data, graph of real data, the y-axis is supply over demand, and the x-axis are the metals lead, manganese, chromium, zinc, silver, silicon, molybdenum, rare earth elements, platinum group metals, copper, lithium, nickel, vanadium, cobalt, graphite. And there are more. But for every single one of these metals by the year 2030, the only metal that we can produce to meet demand is lead. Every other metal on the entire planet we have a supply shortage of. So when I look at all of the stated policy goals, they're unachievable. Right now, they are literally unachievable. Doesn't matter what they tweet, post to Facebook, say at a press conference, say on the stage at the Rackham Theater a few weeks ago, doesn't matter. We do not have the supply of the metals to produce electricity with wind and solar and battery electric vehicles. We don't have them right now. So this isn't possible. This isn't possible. This isn't possible. This is not possible. So what do? I was introduced saying that I have some hope, and I do. What's the solution to the metal supply shortage? What do we need to do? Right? And this is where, depending on the political climate when I give talks, I see smiles or frowns. This is literally the only solution. The only solution to meet the demand is to mine. Because metals have to be mined to be available to build batteries and solar panels and wind turbines. Now, if you've ever flown into the Salt Lake City airport, about 20 miles southwest of the Salt Lake City airport, you see this image. This is taken by a 35mm camera from the space station. And it is one of the world's largest copper mines on the planet. It's called the Bingham Canyon Copper Mine. You can take tours. And it was begun in 1906, is when the first shovel went into the ground. And since 1906, it has produced 45 billion pounds of copper. And every year, they produce 350 million pounds of copper. Every year. Only for electric vehicles, solar panels, wind turbines, etc., we need 1.6 billion pounds of copper. So the math tells us that we need at least 5 of these mines every single year to be producing copper, and probably more like 10 every single year. Well, a question that I get asked a lot is, Adam, can we find those mines? Can we find these areas that God has endowed with copper, and we can dig that copper out of the ground? And the answer is yes. And what I'm going to spend the next few minutes talking about are some myths about mining and other aspects of renewable energy. So I get asked questions such as, or I'm flat out told, there is not enough wind or sunlight to produce all the electricity we need. Exclamation point. I hear this a lot, depending on the news outlet that I listen to, and it's not true. Trust me. We have more than enough wind and more than enough solar, even in Michigan, to provide 100% of the electricity that we need to be 100% electric. All right? When we look at global wind power density potential, it's phenomenal. When we look at the same for solar, it's phenomenal. And blending these two, wind plus solar, allows us to produce 100% of our electricity. We've modeled this for the Southeast Michigan area by using real data from DTE, the total amount of electricity we consume every year in Southeast Michigan, and then we have modeled 100% electricity with no combustion of anything. And what you're looking at here are the colors to me looks pinkish. When you look at the map, you're looking at farms that would be converted to solar. When you look at the map and you see the grayish colors, you're looking at farms that would host wind turbines. Now, say a couple of things. Wind turbines have zero effect on agricultural productivity because wind turbines, you site them along farm edges, property lines, roads. You still farm the same amount of land. Solar farms, and I'll highlight that one of our Board of Regents members, Sarah Hubbard, her father now leases 500 acres of his farm to DTE to produce solar. Because every kilowatt hour that his solar farm generates electricity, he gets a royalty. So you look at the map, and initially you might think, that's a lot. But it's really not that much space for all of Southeast Michigan to go 100% electric. Next one. Solar panels, wind turbines, and electric vehicles are just horrible for the environment. Just horrible. And they must have greater greenhouse emissions than conventional fossil fuels. Not true. So here are data where the y-axis is what we call the life cycle greenhouse gas emissions, or some people refer to it as from well to wheel or from mine to junkyard. If you look, the lowest life cycle emissions are for what? Battery electric vehicles, compared to everything. Compared to green hydrogen, blue hydrogen, gray hydrogen, whatever you want to compare it to, the life cycle of battery electric vehicles has a lower lifetime environmental footprint than every other fuel on the planet. Well, it's too expensive, Adam. I don't want my power bills to go up. It's just really cost prohibitive. Not true. These are data from 2009 through 2020, and all you need to look at is the column on the right is in order of most expensive at the top, least expensive on the bottom. What's the least expensive? Solar and wind. Without any doubt, solar and wind. But Adam, isn't it more expensive to have to build these new solar and wind farms compared to, I've already got a coal plant, I've already got a natural gas plant? The answer is no. Oh, and by the way, these are unsubsidized costs. There's no government incentive here. So without any tax credit, wind and solar are cheaper. When you compare building a new wind farm and a new solar farm against what we call the marginal costs to produce electricity from coal and oil and nuclear and natural gas, or you can think of those as the cash costs, right? If DTE owns a coal-fired power plant, how much does it cost them today to produce that electricity, right? And that cost includes all of their infrastructure, operations and maintenance, salaries, benefits, coffee, Keurig machines, you name it. And what you see, if you look from left to right, for both subsidized and unsubsidized, is there is a dependence on area, but on average, new wind and solar are cost competitive with existing fossil fuel plants, which means that you could close existing fossil fuel plants, build new wind and solar, and the overall cost for your utility will go down, which means cost increases for the consumer go down. But Adam, what happens when it's a hot day in Ann Arbor? I've just come home from top of the park. I walk in the house, left the windows down, left the curtains open. It's really hot and I want to crank up the air conditioning. And everybody else wants to do that too. Now currently, one of the choices we used is called a natural gas peaker plant, P-E-A-K-E-R. And we have the natural gas plant just sort of sitting. It's idle. It's what we call a non-spinning reserve, a peaker plant. And as soon as all of us go home and turn on the air conditioner, they crank that natural gas plant up. Now, there's a lot of data on this slide, but I want to break it down in terms of, well, there are 3 columns. The middle column is the range of costs for solar and wind in different places around the world. The right column are the costs for peaker plants. So using solar and wind now are cheaper than using existing natural gas peaker plants. If you want to see how this is true, these are data for wind electricity as a share of total state electricity generation for the 10 states on the left, the top 10. And if you've followed anything about politics in the last decade, what do we see here? We see that even in states where elected leaders and groupthink say they're against wind, they're not. Because their utilities have realized it's the cheapest way to produce electricity. Now, Texas, their politicians might say one thing, but the reality is Texas is crushing it with wind because it's the cheapest way to generate electricity. And I come from a rural, conservative southern town. There's not a friend of mine who doesn't like it when their electricity rates go down. They all love that. But Adam, what about storage when it's not sunny and it's not windy? You get the theme here, right? Those prices are dropping, literally by the week. And these are the headlines in battery storage space. We're already seeing batteries are cost competitive for long-term storage. 4 hours, 6 hours, 8 hours, 12 hours, 16 hours, 20 hours. Right? We're seeing this as our reality. Well, Adam, that's all great, but I'm anti-mining. Let's recycle our way there. Right? You imagine you're at Kroger putting your cans in and getting your dime back and thinking, oh, this is how we build wind turbines. Recycling can take up some of the demand, but nowhere near all of the demand. So if we look at this graph of data, time is on the x-axis projected out to 2040. The gray is how much, in this case, lithium we have to mine, brand new. And we see the same thing for every other metal. So recycling, without any doubt, will get better, but over the next few decades, it cannot produce the materials we need. Okay, Adam, you've convinced me. We can't recycle our way, but we just don't have access to the metals. Not true. We have plenty of access to metals within the United States, all of the metals that we need, but we don't mine them because of this perception that mining is risky and because it makes great PR to say you're anti-mining. But if you say you're anti-mining, simultaneously you're saying you're pro-fossil fuels. Right? The two go hand in hand. If I am anti-mining, therefore my shirt should say anti-mining, pro-coal, pro-oil, pro-natural gas. All right? And it's not risky. In the last 80 years, 100 people have died at every metal mine in the United States. 100. Think of that compared to the number of people who died driving cars. Number of people who die falling in a bathtub. The risk is really low, and the United States has the strictest mining laws on the planet. So if you're really pro-environment, you would want to mine here where we have the strictest laws of any country on the planet. Well, this all sounds great. What's the problem? The problem, and I'm going to skip a few, is we don't let any mining happen. No mining. We don't want it here, we don't want it there, we don't want it in my backyard, we don't want it in your backyard, nothing. Bumper stickers on cars that contain the entire periodic table that say no mining. Really? I have to scratch my head on that one. Psychologists refer to that as cognitive dissonance. Saying one thing, but actually really wanting the products. My oldest son, who's 20 and way smarter than I am, calls it virtue signaling. Right? Let me virtue signal with putting signs in my yard and t-shirts on my back without actually thinking about it realistically. And this is happening in real time. This is an area of Minnesota that right now it has the potential to be one of the world's largest producers of copper and nickel. Remember those metals that we need for battery electric vehicles? They just took it off limits. Gone. But the mining company who planned an underground mine, which is about the safest way to mine on planet Earth, every year they'd produce almost 100 million pounds of copper, 31 million pounds of nickel, 1.6 million pounds of cobalt. Builds a lot of battery electric vehicles, but Deb Haaland and Joe Biden said no. Not good for the politics. We see the same thing in Alaska. Pebble Prospect would have been the largest mine on the planet and would have produced 320 million pounds of copper every single year. Done. Off limits. So when we look at what we need for these metals, we're simultaneously advocating for build as many battery electric vehicles as you can, build as many wind turbines as you can, build as many solar panels as you can, but you can't mine anything anywhere. Right? It doesn't add up. All right? We look at U.S. lithium potential. We've got a lot. In the state of Maine, they have a lithium deposit there that would allow this to happen. State of Maine, by 2045, wants to be carbon neutral. Every vehicle is a battery electric vehicle. This rock that exists above ground and below ground in the state of Maine, only 1% of that rock could build enough battery electric vehicles for 100% of the cars in Maine. 100%. And the rest of the lithium could produce 58 million more battery electric vehicles. But in 2017, Maine banned mining. Banned it. Toughest mining laws in the entire country. You got to think. Thacker Pass, in the news a lot. The Biden administration greenlit it. DOE loaned them $650 million. Federal judge within the last few days says, yes, I think it can move forward. It only produces enough lithium for 664,000 vehicles. So for 8 million, we need Thacker Pass and 12 more. Literally now to start going into production. Cobalt, we only have one mine in the entire country that produces cobalt. They actually ship all of the concentrate to Brazil where it's processed and purified to cobalt. That's only 1 million pounds. It's 23,000 battery electric vehicles. You sort of see that the math really doesn't add up. We know how much we need, but we're not permitting the mining to produce the metals. On average in the US, it's a decade. It's a decade from when a company says, I have found a particular place within the United States that is endowed in lithium or nickel or copper or cobalt. It is 10 years before they get a permit to begin mine construction. It's 2023. That would be 2033. All right? You can't make 2030 8 million battery electric vehicles. Who has seen the writing on the wall? It's China. China, over the last 20 years, has planted the seed around the world outside the United States and also investing in some mines in the United States. And they now have the potential to acquire all of these metals which means right now we're 100% dependent on China for all rare earths, right? And again, rare earths, how can they be important? Well, they make permanent magnets that make the motors that you use to drive a battery electric vehicle. Yttrium is chemically considered a rare earth, and if you've ever seen night vision goggles, you need yttrium to make night vision goggles. So everybody in our military who has night vision goggles, that night vision is courtesy of China. When we talk about environmental justice, there are some significant challenges. So Thacker Pass is probably going to go forward because it's a great political move for the Biden administration, even though it literally is 1/12 of the amount of lithium we need. But it also sits on land that is sacred to indigenous communities. It sits on land where white colonists murdered a large community of Native Americans. That's not me. Oop. Should I unplug and replug? Okay. Let's try it. All right, so these are real issues. You know, I gave a presentation recently to the Tribal Energy Council, and they're looking at renewable energy through the lens of where are all of the metals. If you look at a map, pretend you're looking at a map of the United States, all of the metals that we need for renewable energy are located within Native American reservations or within about 40 miles. So Native Americans, there's tremendous fear of a new wave of white colonialism, where we steamroll over them because we need the metals, without helping them build the infrastructure that allows them to benefit long-term from producing those metals. So from an environmental justice perspective, there's a lot of real concern. But again, you take a step back and say, what do we need to do in order to transition from our current energy infrastructure to one that is 100% electric, where all of the electricity is generated only from renewable energy resources? Maybe? All right. So these are real issues, and I'm not proposing we steamroll and extract. I'm suggesting that the broader we need to have these really important conversations. Same thing for the cobalt mine in Idaho. It's on land considered sacred to indigenous communities. And it sounds great to ban the mining here. That's great PR. They're great tweets. We've taken this off the market. We're not going to allow mining here. And if you do that through an environmental justice lens, you're also then saying a couple of things. I'm fundamentally anti-renewable energy because I won't allow the mining to happen to make it. Or I am pro-white colonialism, where we impose our will on African countries and Latin American countries and Asian countries and force them to mine what we want. Right? Either way, it's not what I would choose. So this is that map I asked you to imagine. Native American communities are concerned. But what I see is simply a lot of PR and political rhetoric without actually addressing the problem. So, 2 slides left. And if I can figure out how to make my mouse work. Oh, there we go. Promised myself I wouldn't curse at all, and that's only 1. And those who know me probably are shocked that I haven't cursed more. Okay? We've got a choice. Right? We're literally at that point. We've got a choice. We have the recipe to make all of this happen. We do. We know how it needs to happen. Right? What are our biggest challenges? Political cycles of 2 years and 4 years. Right? Lawyering up is a major problem. 1960, United States, there was 1 lawyer for every 650 of us. Now there's 1 for every 250 of us. 1/3 of our House of Representatives are lawyers. 50% of the Senate are lawyers. It's way too many for me. Because what they know how to do is sue. And what we're seeing in real time, that 10 years of permitting, is lawsuits. It's not on the mining company's perspective. It's all because we have groups that simultaneously want 100% renewable energy and simultaneously disallow any of the mining of the resources to make that reality possible. So something has to give. All right, I mentioned this concept in psychology of cognitive dissonance. This is what we see. We see it on this campus. We see it in the School for Environment and Sustainability. We see it in the Department of Earth and Environmental Sciences. We see everybody lined up for what sounds good, what allows them to signal some virtues a little bit more, what makes for great tweets. And I'm over in the other line saying, but hey, we need copper, we need nickel. Like, I'm not making this up. Where is it going to come from? Oh, you don't want to mine it in Minnesota? You want to force mining to happen in Zambia, or in Colombia, or in Brazil, or in Thailand? Okay, then don't tell me you're an environmental justice warrior, because we have the potential to do this. The United States is 4% of the world's population. We consume 15% of the world's energy. If we do it, others will follow. That's always been, for the last 100 years, what we've seen happening. And we have the potential to do that now. But I think there are too many people in the wrong line. And we need to sidestep, and we need to start advocating for what fundamentally controls the entire supply chain for all renewable energy, which is the metals in the ground. And in the United States, we mine in a phenomenally clean way. I'm not saying there's never the potential for environmental degradation. I'm not saying that. You're clearly altering the environment when you mine. But our level of oversight and third-party consultants, et cetera, et cetera, et cetera, we can do it better here than anywhere on the planet. And we have to start letting it be done in order to achieve the goals that everybody wants. Thank you.
Thank you, Adam, for wonderful insight and presenting us that conundrum and maybe some directions in which make sense. There's a lot to unpack there, and thank you for massive data and charts.
And I'll just say, if anybody wants these slides, I'll share them. Yeah, happy to provide these. I actually have, if you really want it, I have my entire Natural Resources, Economics, and Environment course on my YouTube channel for free. I don't think I told Michigan that, but Myron, you can't go back to the dean's office and mention that. It's for the public good. But yeah, I'm happy to share these slides with anybody who wants them.
Thank you very much.
And I also know, as a few people know, I do enjoy meeting for coffee. So if anybody wants to meet, always happy to do that.
All right, so we've got a ton of questions, really raised a lot of issues which surround this complicated topic. I don't really know where to start, but let's maybe with the big picture question, is nuclear energy part of, it's not a renewable necessarily, but is it part of the equation in the future? What's your stance on nuclear energy?
I think nuclear fusion's a pipe dream. If there's currently a DOE public-private partnership in southwestern Wyoming to build a new small-scale modular reactor, which is, interestingly, what the Department of Defense and DOE built before there was DOE in the 1950s. When we first figured out, if you ever go to southeastern Idaho, just outside of Idaho Falls, you can go to what's called the EBR-1, and it was the first test reactor where the Department of Defense figured out how to harness the energy released during nuclear fission to use that to boil water, to turn turbines, to make electricity, and they have the 4 light bulbs there. And I'll sidestep and talk about progress. They did that in 1952. When they did that, they had every male member of the staff sign their name on the wall, including the male janitor. They didn't allow any women, even women scientists, to sign the wall. We've made a lot of progress in 70 years. So they were building small-scale reactors, and just to give you a sense of energy, 1 atom of uranium-235, when it undergoes natural fission, releases 202.5 million electron volts. 202 million. I think there can be a place for these small-scale reactors if the company TerraPower in Kemmerer, Wyoming can demonstrate that they can build it in a realistic time frame. It has the potential, but I don't think we need it.
And also part of the bigger picture is geothermal energy.
Yep, I didn't mention that, but I'll say, and some people in the room, I know John is on board with this, was in the paper recently, photographed with a nice little Michigan thing next to your geothermal system I saw. Geothermal has to become the way that we heat and cool our spaces. Right now, 50% of all winter heating in the United States is natural gas. A majority of our hot water heating is natural gas. So we have to move into 100% geothermal heating and cooling, and it can be done. As an example, Ball State University in Indiana, their campus is about the size of our North Campus. They are now 100% geothermal heating and cooling, 100%. They were a DOE pilot project almost a decade ago, right? So they led, and Michigan is still trying to figure out, like, where are they? Because we can't find out how to get there. We have the recipe, so that has to become standard. And that gets to one thing I'll mention, because I know Jane has geothermal heating and cooling at her house as well. You make this standard. This is where California is trailblazing. If I'm going to develop a new property, that property's off the grid, right? That property has really thick walls, right? Think about adobes. Adobes were built with really thick walls. You have geothermal heating and cooling. You have solar across the roofs, right? And that's what allows you to heat and cool that space. So I think, yeah, there has to be a much larger role for geothermal.
To add to that question, does the drilling expertise developed by the oil industry help in any way toward that?
Absolutely. You know, I mean, I have a lot of friends who work in the oil and gas industry. They're really, really smart people. Right, a lot of PhD students from this campus in the Department of Earth and Environmental Sciences, they're incredibly smart. You know, I've seen some of them take their candidacy exams, and I'm glad I'm not having to be the the examinee. So what do they offer? They offer tremendous technical expertise, right? I mean, think about a floating oil platform in the North Sea that just floats out there, and at the bottom of the water column, 1, 2, 3, 4 miles, they're drilling into the subsurface another 1, 2, 3, 4 miles, and then laterally. Whether or not you're pro-oil or natural gas, the technology is there. So I think that their smarts and their technology are there. And honestly, looking at their record profits, the capital's there, right? I mean, if I just made $35 billion and I'm the CEO of Chevron and I cleared $58 billion as profit for ExxonMobil, they have people now thinking in this space. They're just not moving fast enough, and that's where the public part of these public-private partnerships comes into play.
Thanks for that series of questions, by the way, really good questions. And also along that line, the hydrogen economy is in the news a lot. What's your feelings about, is that a step on the road toward toward your goals? Or
it has potential. So with respect to hydrogen, if we're talking about green hydrogen, where it's 100% produced with renewable energy, it has potential. Right now, I don't think it has the potential to be scaled up as rapidly as wind and solar and grid-scale battery storage. You know, there's a company in our backyard called Our Next Energy, ONE is the acronym, and they're already now, last year, they developed a new prototype battery that they put in a Tesla and it drove 700 miles. And that battery is designed for light commercial vehicles. So think about all the Amazon trucks, the Postal Service. So I think that if mining operations can be permitted not at a speed that sacrifices the environment, but at a speed that is much faster than today, right? We need to go from 10 years to 1 to 2 years. And we can produce the metals. I don't think we need hydrogen. I think it falls under the same category of carbon capture, utilization, and storage, which on some level is the holy grail for the oil and gas industry. Right? You combust it, you put it in the atmosphere, you suck it back out, you put it underground. You know, so they're sexy, they're attractive, they're great for sound bites, but they haven't been able to demonstrate the ability to scale in the time span we need them to.
Could you make a quick comment on carbon credits and how that's a somewhat controversial topic right now, as you probably know?
I think they're PR greenwashing. And our university is guilty of that. You know, our university likes to advertise how much renewable energy we, quote, use, unquote, and the EPA allows them to do that in legalese. But our university, as we sit here right now, none of this is renewable energy. We're buying it in other places, so it has a positive impact of taking offline currently existing coal and natural gas, but you can't carbon offset your way to 100% electricity. At some point, you have to get off the pot, and right now, Michigan seems glued to the pot, as does many other places, and you gotta just make the decision we're gonna move forward. Sorry to use that analogy if you don't like that one, but where I come from, that works really well.
Right, thank you. So this is coming to a physics question, and that is the distribution of solar panels at the scale of a solar farm, you know, gigawatt level. Mm-hmm. How does that affect the albedo of the planet, the reflectivity? Is that significant?
So that is outside of my area of expertise. All I can comment is that everything I have read, especially with new solar arrays that use much smaller panels, right? So literally as we speak, engineers are going from this to this, and they'll continue to make improvements, right? It's never going to be infinitely small. There's also a lot of growth in what we call agro-photovoltaic systems. So you build solar arrays on farms at a height of give or take 3 meters, about 10 feet, which allows for grazing, and it allows for the growth of crops that need some shade. Everything I've read, it will not be a problem with respect to the total planet's albedo.
Yeah, I think you kind of touched on that when you gave an estimate of the amount of coverage that you would need to, for example, even in Michigan,
right.
It's fairly noticeably small as a proportion of the total surface.
Right. I mean, you know, one example I'll give here on campus is we have 2 18-hole golf courses. Jane, you knew I was going here. Now, I'll preface it by saying golf is a relic of systemic racism. That's not me. That has been well documented by dozens, if not hundreds of studies. Harvard Business School had a great study on this. If we look at golf and tennis, they were effectively created so that white people could play those sports and black people were not allowed. We have 2 golf courses. If we converted those golf courses to grid scale, farm scale, renewable energy, they would generate more electricity than this entire campus uses in a year. 2 golf courses, we own them, right? One is right over there, and one is right over there. We own the land, eliminate golf. To me, that is diversity, equity, and inclusion, eliminating a sport that is a testament to systemic racism, and convert that land to solar, which we say we want. Right? That is like cha-ching, cha-ching. But the University of Michigan won't do it. We've proposed this to the last president. We've proposed it to the current president, and they say the golf courses are off limits, which again, you're like, God, systemic racism? Only white people? Really? Again, it makes me scratch my head. But that's what's possible. Our whole campus, 2 golf courses. But we won't do it.
So these are all great questions. So here's another interesting question. Is there a gap between the mine and the final product, mining ore, I think that refers to? And can you talk about converting ore to metal and the cost of smelting as part of the equation?
Yeah, so right now globally, excuse me, the average length of time to find a particular ore deposit for whatever metal it is and build the infrastructure and make that metal available is 16 years. That's 2039, right? On top of that, you include permitting, and you're into the 2040s. If you sum the entire life cycle emissions for all of the metals that we need to build renewable energy, they're 1 to 2 orders of magnitude lower, less than fossil fuels, including smelting, digging, trucking, you name it. Everything involved in that pit in Utah to where I have copper in my phone has a lower overall carbon footprint than fossil fuels.
And is there a kind of toxic burden to extracting metal from ore that has to be done on site? Well, not necessarily, I guess, on site, but I visited gold mines and things like that where they, at least in the past, they use things like mercury quite a bit to extract the gold from the. Is that's a concern of the public?
Absolutely, and it's justified. If we look at some of the methods that we use to extract gold from ore, we use cyanide. And there have been a very limited number, but there have been a few really horrific accidents where cyanide has polluted waterways. One was in Romania about a decade ago. And so there's always going to be risk associated with taking a rock out of the ground and physically and chemically separating the metals in that rock from everything else. There's always a risk. What I think we have to do is evaluate that risk with the risk of doing everything else, right? So the risk of 20 million people in Lagos being under sea level in 30 years, the risk of most of Florida being under sea level in 30 years. Most of Houston is already below sea level, right? And so there's risk in all of our choices, and we have to, in some way, rank those risks and make the decision about, okay, if this is the goal, and these are all possible, plausible pathways, which one has the absolute lowest risk? And I visited a lot of mines also in more developed countries and less developed countries. And without any doubt, mining as it's being done in the United States, in Canada, in Australia, is the standard. And yes, there's still risk, but the overall risk is much lower than it is elsewhere.
Right, thank you. So you've written several books on the economics of renewable energy, the relationship between economics, manufacturing, and such. So you're the right person to ask this question. So when the grid will have to be expanded to accommodate so many million electric vehicles, for example. So how much copper is needed to expand the grid to give the capacity that's needed to make this transition into electric vehicles?
So that's what I included in one of those slides where I use that Bingham Canyon mine as an example. They produce about 340 million pounds of copper every year, the final product. And we need probably on the order of 10 of those every year for the next few decades. Now, something I remember now I didn't say is, it's important also to remember that once we build this infrastructure And engineers who are incredibly bright people, including our engineers that operate a battery lab on North Campus, they figure out how to recycle all of the metals in our technology at a 100% level. Then the amount of mining goes down, right? So we get to something that is referred to as a circular economy, right? Once you build out all of this infrastructure, the copper in my phone doesn't care if I take it out of my phone and put it in a laptop, or if I put it in wires that run through this building. So metals, right, they don't have feelings. So once we build everything, we don't have to ask the metals permission to say, you know what, I'm going to take the smartphone. And by the way, on average, smartphones, there are about 75 elements of the 118 that we know embedded in the supply chain of a smartphone. If I can disaggregate and chemically separate them all, I can use them again, and again, and again, and again, and again. So what we need almost an effort similar to what we saw with rebuilding and building new in the 1940s in order to defeat Germany and Japan. We need a similar scale of effort with new Rosie the Riveters, and also to accept that we have to extract all of these metals at least for the next few decades.
So you see that as a kind of shorter term or medium term problem rather than one that'll kind of keep getting worse and worse into the future because recycling will
get better.
Kick in at some point.
Yeah, I mean, I'm 51, and I can remember growing up in North Carolina when you didn't recycle anything. Everything got landfilled. And then I remember it started with paper, and then it was aluminum cans, and then it was glass. And today, what we know is that companies recycle those products because it's economically beneficial. Making aluminum from a mine to a can is really energy intensive. It's the greatest expense for any company such as Alcoa. It's a much less, by an order of magnitude, less energy intense process to recycle. So they want to recycle everything, so they pay less for the virgin mine material. The same thing for steel. And what we're now essentially at a tipping point is when there's going to be some engineering group somewhere that's going to do something, and it may be an accident, right? Happy accidents. And it's going to be I just figured out how to separate the rare earth elements from copper and gold and everything else in the phone, and if we scale it up, the price will drop, right? There's something in economics that's referred to as Wilson's rule or Wilson's law, that as you produce more things, the overall cost drops. And we'll see the same thing. When we look at the price of any of our technologies, I remember my wife in 1993, her father bought her an IBM laptop from what was then Price Club, what is now Costco. It was $1,500 and it had a floppy disk with a 386 processor. Everybody today on this campus would laugh if you handed that to them. But that was already better technology than what we used to put people on the moon. So what we see is that if we move in the right direction and we look back, we can see that progress happens pretty quickly. What we have to do is now start moving faster in the right direction.
Well, that was incredible insights. I thank everybody in the audience and also online for asking so many questions, which are really interesting. We have a number of questions left, so we're coming up on the noontime hour. So I'd like to, before we conclude today's presentation, I'd like to thank Adam for a fantastic talk and illuminating this important topic.
Thank you.
I'd also like to take a moment for a huge shout out to our production staff, especially Carl Cole and his team from Michigan Media. Monica Wood, especially for these demonstrations are always a really great part of a Saturday morning physics, and the ones you chose today illustrated the points perfectly, so thank you for doing that. That also includes the team of wizards from the Warren Smith Demo Lab who are responsible for developing all these demos and putting them on for us. Our communications director, Carol Raybuck, for organizing and for bringing in the donuts back into the Saturday morning physics orbit. That's great. And I also want to thank some of our sponsors for Saturday morning physics, which is supported through the generosity of the following donors: Drs. Lyle and Lois Tiffany, the Hideko Tomizawa Endowment, the Van Loo Family Endowment, the Bernocchi family, and the Department of Physics and Friends of the Physics Department. Thanks again, Adam, for a fantastic talk. We look forward to seeing you all again after the spring break on March 11, when the lecture demo staff will present a family-friendly extravaganza called Physics Goes Boom. So that's on the 11th in this auditorium here. And we wish you a good break, and we'll see you after the spring break. So thanks again.